Okay, this problem says a disk of mass 2 kg and radius 60 centimeters with a small mass of 0.05 kg attached at the edge is rotating at 2 revolutions per second. The small mass suddenly separates from the disk. What is the disk's final rotation rate? Right, so here's the top view of the disk, and the disk is rotating about this axis, and we have a small mass on the edge. And so the disk has a mass of 2 kg and radius of 0.6 meters. And we'll say capital M for the mass of the disk, 2 kg, and this mass is small m. And little m is 0.05 kg. And omega is 2 revolutions per second, and each revolution is 2 pi radians, so 4 pi radians per second. Alright, so what happens is when the mass falls off, so this is omega initial, and when the mass falls off, omega final, angular momentum is conserved. So I initial omega initial equal to I final omega final. I initial is the moment of inertia of the disk plus the moment of inertia of the little mass sitting on the end, so which is 1/2 m r squared plus little m r squared. So this is equal to 1/2 2 kg times 0.6 meters square plus 0.05 kg, and that's the little mass, times 0.6 meters squared. And so this is 0.36, which is the moment of inertia of the disk. This is that term. Or should I say 0.36? 0.36 plus this is 0.02. Okay. Kg meter squared. So you see most of the moment of inertia is still coming from the disk. The moment of inertia of this guy is very small. Okay, so this is 0.36, oops, 38. It's equal to 0.38 kg meter squared. All right, let's add a page. Okay, once the little mass falls off, the moment of inertia, the final moment of inertia is just the mass of the moment of inertia of the disk, which is 0.36 kg meter squared. All right, so I initial omega initial equal to I final omega final. Omega final is what we want. Okay, oh, we can give the rotation rate in revolutions per second. We'll do that. Okay, so omega final is I initial over I final times omega initial. All right, and so you can see that from this problem, and you can I final. You can see that if the final moment of inertia is smaller than the initial, this number will be bigger than 1, and the final angular velocity will be greater. So this is 0.38 divided by 0.36 and the units are kg meter square, times initial angular velocity was 2 revolutions per second. Okay. So final angular velocity, since the moment of inertia decreased, the final angular velocity will work out to be greater. So 2.11 revolution per second. So that's the final angular velocity. All right, that finishes this problem.